Okay, today's the 11th, and let's do this homework question. This is an integral, e to the 3x plus 3e to the x plus 3 all over e to the x dx. What you want to do here is split it up, okay? You want to split this up into 3 parts. E to the 3x over e to the x is e to the 2x. 3e to the x over e to the x is 3. 3 over e to the x is 3e to the opposite of x. And what you've got here is the integral of that constant, and then you have 2 other integral of e to the u forms. So, let's do them. The first one is e to the u du form where u is 2x. Here, let me write it out. I'm going to split it up this way. Okay. And now, e to the u, where u is 2x, the du is 2 dx. I need to multiply by 2 and by 1/2. By doing so, I end up with 1/2 the integral of e to the u du. That's the form that we want. Okay, e to the u du form. The next one is just the integral of dx, which is just plain x. And the last one is an e to the u form where u is opposite of x. The du is a -1 dx. Multiply and divide by -1, but that's the same as multiplying by -1. So we end up with a -3 e to the u du here. Okay. 1/2. The integral of e to the u is e to the u. In this case, the u is 2x. The integral of e to the u is e to the u. In this case, the u is the opposite of x. And that's your answer. Okay? Okay? Yes, Jim.
Yeah, I got another one.
Go ahead.
It's square root of tan 5x.
The integral of that?
Yeah, times secant 5x squared.
Okay. All right. What you want to do in every integral virtually that we do, you want to look at that integral and identify an integration form. Okay? We have, what, 10, 12, whatever it is, integration forms. We're going to add a couple more today. We'll add a couple more the next class when we do Cinch and Kosh. Okay? What does that mean? That means looking at this integral, identifying a u and a du to go with it, okay? And seeing that you have one of those integration forms. We've got the square root of tangent 5x by letting u equal the tangent of 5x. Du is equal to secant squared 5x times 5. Now we do need a times 5 in there, but that's the form. The form is a u to the n form. That's the kind of thing, after doing enough of these, hopefully you'll be able to see, okay? So, by letting u equal tangent, and almost always, if you have a function of x in grouping symbols, and the square root, the radical acts as grouping symbols, that's your u, almost virtually always, okay? That's your u. If u is equal to tangent 5x, du is secant squared 5x times 5 dx. And that's fine. We have a secant squared. If we don't have the secant squared, forget it. We can't do the problem this way. There may be another way of doing it, but it's certainly not obvious, okay? But because we have the secant squared to serve as the du, we have a u to the n form. So, multiply by 5, multiply by 1/5. We have 1/5, the integral of u to the 1/2 du. Okay? I strongly recommend when you do these integrals, you take the time to write this step out. Okay? E to the u forms here. u to the 1/2 here. Write the form out, okay? What's the integral of u to the 1/2? U to the 3/2 times 2/3 plus c. That's equal to 2/15 u tangent 5x to the 3/2 plus c. Okay. And if you were to take the derivative of this, guess what? You'd end up exactly with what you started with. Okay. Yes?
So you did the du and got secant squared 5x times 5 dx.
Yes.
You then went back to the integral?
Yes.
You just wrote a 5 in it,
Yes, I did.
but it never got used.
Yeah, it did.
Placeholder.
Well, no, this 5 got used. This 5 is in here with the du. I need this 5 in order to do this integral, because I need the secant squared 5x times 5 dx. And because I need I had to write it in. I had to multiply by 5 and compensate by multiplying by 1/5.
So it's 5 over 5. So it's
Yeah. So it's 5 over 5. This 5 is in here. The other 1/5, the compensation, is out here. Okay. How we doing? Okay. Any others? Let's do some more. Yeah, go ahead, Sam.
So it's in parentheses 4t squared minus 5, and the parentheses is squared.
The integral of this?
The integral, yeah.
Oh, this is nasty. Okay, well, it's not that nasty. Here's the thing. I just got through saying that virtually all the time, when you have a function of x, in this case a function of t, inside the grouping symbols, that's your u thing. Okay? The problem here is, if I had a t out here, it would be perfect. I would let u equal 4t squared minus 5. The d would be an 8t dt, but I don't have a t out here. Okay? I can't do this problem that way. There's no t here. And I can't just multiply by t and multiply by 1 over t. That's not allowed. You're not allowed to take that variable out front. Okay? It changes the integral. You can't do it. All right? You're allowed to take a constant out front. That's what you're allowed to do. So we can't do it that way because we don't have that t. What must we do here?
Multiply it.
Yeah, we have to multiply it out. Okay. So multiply it out, 16t to the 4th minus 40t squared, twice the product, right? Plus 25. Just multiply the thing out. Then integrate it term by term. 16t to the 5th over 5. 40t cubed over 3. 25t plus c.
That's the answer I keep putting in online, but it doesn't work. It says that's wrong.
Well, wait, who's got a laptop? You got a laptop? Wait, Jacob, can you get this exact question? Which number is this, Sam?
It's in the first homework set, I think 13.
13?
Could be wrong.
1 second, sorry.
Okay, this is
14, you said?
13
13?
or 14, I don't know. Looks kind of like that.
if you can find the exact one, this is the answer.
This is not, I mean, it's not the exact one, but
Well, let's do
I
this.
found it.
All right, well, what do you have there, Jacob?
I just expanded it, and then I saw that.
What's that?
All I did for mine was I expanded it, and then I.
Yeah, did it out.
Yeah.
All right, I just, you,
Well, that's it. Before we even did that, I wrote what I've been drawing in for the
Oh, let me
answer
see.
right here.
I mean, I can check
Before I even
Wolfram
asked.
and go
That's the
that
answer I
way.
keep submitting. And it doesn't.
Check it.
something wrong. You're
Okay.
submitting something wrong. Or, I mean,
That's the exact form right there.
Capital C.
Oh, you know what it might be? What I did was I put x instead of t. Because I put x instead of t
he's
inside.
got a
of the
T
syntax.
there, he's got a T here.
Right, but
I'd have to see it. What's that?
Yeah.
You have to put capital C because if you put a small c, it
No,
doesn't work.
I know. It's,
Yeah, that's
Really?
what happened. Yeah, that's what happened to me the first time.
It tells you though.
Yeah, if you don't have a c. But what I did the first time for this one is I.
Well, that's the right answer.
Yeah.
All I can tell you is you're putting it in wrong something. You're doing something wrong.
Alright.
And I don't know what it is. Wait, so Brendan, you know what you in there somewhere? Oh, well, no, you're playing a Pokemon game.
Had an answer like
Oh, did- Yeah.
I put it in Wolfram and it gave me the same thing that you got.
All I can tell you, Sammy, is
something's wrong.
You're putting it in wrong somehow. I don't know what you're doing.
Yeah.
I'd have to see it though. I'd like to see it. Wait, Carlos has got an idea. You have that exact problem?
No, I checked.
Yeah.
I checked it too. Wolfram.
Yeah, I know, I know.
Screw it.
You know, no, don't say that.
Check to make sure that you're putting in T and not X. Because I did that the first
Yeah.
time. I was like,
All right.
I did this right, what's wrong? And that's all it took to.
Um,
Can't check it.
I don't know what to tell you, except, how many tries have you had already?
I think I have unlimited on that one. I've submitted, just because like I put the right answer and it just wouldn't take it, so I just tried a bunch of weird variations that I wouldn't know why it would be it, but it still lets me put things in.
How many
Okay.
tries do we have anyway?
I think it's 5. I think it's 5 submissions.
Oh, then I think it's close.
Okay, well, I can do things. I can delete your submissions, or I can do something. You know what I could do? Actually, Sam, when I'm done here, okay?
Eh?
When I'm done, we'll check out my computer. I can look at what it's saying for you. I can check it out, okay? So we'll go to my computer, we'll check it out, all right? We'll check it. All right, any others? Carlos, you have one?
Yeah, it's like that one, but it has that symbol and 16 over x.
Okay, the integral of what now?
16 over x.
16 over x?
Yes,
dx?
yes.
Carlos, what are you doing? We haven't done it yet. This is today. We're going to do that. It's 1 over u du form. Oh, well, we're going to do one. I did mention 1 over u. Well, okay, let's do it. But this is what I'm going to do today. I'm going to use this 1 over u du form. But we can do this. This 16 you can take out front, because we have talked about this. What's the integral of 1 over x? It's the natural log absolute value of x plus c.
I put that number exactly like that. It's marked.
I know, students tell me this all the time. Burns, I put this in exactly like you said, you bozo guy, and it's wrong. So that means, you got an absolute value in there?
Yeah, it's here.
Oh, you have it right there?
Because there's an Alex, you click for natural log and it has the absolute value.
Yeah.
Oh, yeah, that's
Yeah,
true.
we're gonna-
You're using the natural log, they giving you the value?
And then I use X for the third.
Oh, that's
for
wrong,
some
something
reason.
looks wrong, that X is
Yeah.
too funky. See that X you got there? That's a funky X. Can you get in there like that and put a little normal X in there? I don't know where you got that big giant capital X, that's the problem. Wait, why do you got another plus here? Oh, they're giving you the plus. But that X looks weird.
It has to be.
I think you should have lowercase x. I don't know if that should make a difference. It shouldn't really.
Oh, yeah.
No, it's right. Yeah, they gave you the C. Maybe they gave you the C.
No, I figured it.
You did?
I was using T's properly, and then I switched to
Oh,
X for
that's
some
it.
reason.
All right, that's it. Listen, that'll happen. You know, no big deal. But if you do have a problem with the website, and you before you destroy your computer, you know, you may want to send me an email or something like that saying, Burns, I'm putting it in correct, but it's marking it wrong. And I have the ability to go in and see what you're putting in, and so I can fix it up. Okay, so let me know. Okay, before you get all frustrated and mad at your computer or website or at me, all right, let me know, and we can do it. All right, any other questions? Minus? No questions? All right, let's do a numeric integration. Numeric integration is used to do an integral that can't be done any other way, okay? I mean, we have the ability to do an infinite number of integrals, exactly. But there are, again, an infinite number of integrals which we can't integrate, all right? You simply can't do it. We can't do it. Mathematica can't do it. So when you give an integral like that to Mathematica, it'll say it can't do it. Now, if you have a definite integral, an area under a curve, what it will do is use a numeric approximation for that area under the curve. I'm going to derive the trapezoidal rule, which is one numeric approximation. It's not the one that Mathematica uses. It uses a variation of a Simpsons rule, which is a little bit more accurate, but it's the same idea. Okay? So what I'm going to do is derive the trapezoidal rule. Okay? Let's take a look at this. I'm going to go right for the general case here. Let's suppose we have some function of x over some interval from a to b. And what we want to do is get an approximation to what the area under this curve is, okay? An approximation. Well, we've already done such a thing by using left endpoint rectangles and right endpoint rectangles when we did y equals x squared a week or so ago. All right? And I think I mentioned at the time we could get a better approximation by taking the average of the two, because one will be too high, one will be too low. If we take the average, and the average of those two rectangles is a trapezoid. And that's what I'm going to do here. We're going to divide this into trapezoids, okay? We're going to take the interval into n sub-intervals, equal subintervals. They don't even have to be equal, okay? But we're going to make it a little bit easier, we're going to divide this up into n equal sub. Carolina, I know, I see that. You may want to sit closer. You don't want to sit closer? Not now, now that I've embarrassed you, huh? I'm sorry. But it's up to you. It's your call. It's your call. You can do whatever, okay? Is it really bad? Wait, you got glasses on and everything.
I know.
You need...
No, it's okay. I think, is that a B and a 0?
Yes, it is. Oh,
Okay,
sure.
so yeah, I can see it.
Okay, yeah, that was convincing. Is that a B? Or? Yeah. All right. Okay, so let's take a look at this. We're going to divide this up. Each one of these I'm going to call delta x. Okay. Now, delta x, if I divide this up into n parts, it's going to equal, what will delta x be equal to? If I divide the interval from a to b up into n equal subintervals, what will the width, delta x, be of each of these subintervals?
One over n.
1 over n is a start, but 1 over n would be correct if the interval were of length 1. Okay? But now I have an interval from a to b, and I'm dividing that up into n equal subintervals.
It would be b minus a over n.
That is correcto. Nice job there. B minus a, the width of the whole interval, divided up by n subintervals. So I have a delta x. Now, let's take a look at this trapezoid. Okay. This area, this particular area, this ith area, say, is going to be approximately equal to 1/2 the height times the sum of the bases. That's the area, that's the formula for the area of a trapezoid. It's going to be 1/2 the height. Now the height is the distance between the parallel bases. That would be the delta x part. Times the sum of the bases. Well, if I call this one here x sub naught and x sub 1, and this is the ith one, put some dots in here too, x sub I, and x sub I plus 1, etc., and keep on going. What will this height be right here? That'll be one of the two bases of that trapezoid. What will that height be? If this is x sub 1 down here, that is the, yes, Brendan.
F of x sub 1.
Thank you. That's f of x sub 1. And the second one will be f of x sub I plus 1. Okay? That's the area of that trapezoid. Okay? Here's what I'm going to do. I'm going to take the sum of all these trapezoids, okay? We'll add them all up to get an approximation for the area under this graph. So, the area in terms of n trapezoids would be approximately equal to the first one, which would be 1/2 delta x, f of x sub naught, f of x sub 1. That would be the first one. It has this form. Plus the second one, 1/2 delta x, f of x sub 1, oops, 1, plus f of x sub 2. That would be the second one. Is everybody with me? Everybody see what I'm doing here? Are you with me? Kinda, sorta. Okay. What I did here, I gave you the general form for the ith trapezoid, but now I'm starting at the beginning and adding them all up. Okay. So, and each trapezoid, the area of a trapezoid is 1/2 the height times the sum of the bases. The height of each trapezoid is delta x. The height is the distance between the two parallel bases. These are the two parallel bases. Okay? And that's what I'm doing. So I'll do one more. 1/2 delta x, f of x sub 2, f of x sub 3. And then the last one we have is 1/2 delta x. Now, this would be x sub n right here, right? So it would be f of x sub n minus 1 plus f of x sub n. Okay? Okay? That's the approximate area under that curve in terms of those n trapezoids. So here's what I have, the area in terms of n trapezoids. Now what can I do? I can factor out a delta x over 2. And I have 1 f of x sub naught. And how many f of x sub 1s do I have? 2. And how many f of x sub 2s do I have? 2. I had 2. I said 2. Okay. Hand didn't listen there. Plus. Now, how many f of x sub n minus 1s will I have? No. 2 still. You only see one of them here, but the one before that is an x sub n minus 1 as well. And how many f of x sub n's do I have? 1. This is the trapezoidal rule. Okay? That's the trapezoidal rule. The delta x is b minus a over n. So here's the trapezoidal rule. I'm going to write it out. Everybody else set here?
No, wait.
Oh, okay. We all set? So, trapezoidal rule is this. The area in terms of n trapezoids, okay, is approximately equal to b minus a over n times 2 times this sum. F of x sub naught, 2 f of x sub 1s, 2 f of x sub 2s, 2 of f of x sub n minus 1s, f of x sub n, like so. That's the trapezoidal rule. Oh, let's see how good it is. Let's do an approximation of something. Well, I could do x squared. Let's do x squared, okay? We'll do x squared. We'll keep it simple. Let's do a function is x squared, and let's suppose the interval is from 1 to 3. So we want to do an approximation of the area under this graph, y equals x squared, from 1 to 3. We want this, okay? And the more intervals we take, obviously, the better the approximation, okay? let's take, let's divide it up into 4 parts. Okay. Okay. So, here we go. This point right here, what would the coordinates of this point be? 1.5. 3 halves, 0, 1.5. I like fractions better, though. 3 halves, 0. Okay. This point?
2.
Thank you. This point?
2.5.
5 halves. Good deal. And then 3. Okay. What's the delta x in this case? The width of each one of these? 1/2. Thank you. Okay. So, our area in terms of 4 trapezoids is approximately equal to b minus a, 2 times 4, n is 4. We got 4 parts. Okay, n is 4. F of 1. F of 1, I'm going to write it out, plus 2 f of 3 halves plus 2 f of 2's plus 2 f of 5 halves plus f of 3. Okay? Poor planning in here. Okay? Okay. All right. So the area in terms of 4 rectangles is 2 over 2, it's 1/4. F of 1 squared is 1. 2 times f of 3 halves squared is 9/4. 2 times f of 2 squared is 4. 2 times f of 5 halves, that's 25/4. And then 1 f of 3 is 9. This is equal to 1/4. 1 plus 9 halves plus 8 plus 25 halves plus 9. Okay. So our area in terms of 4 trapezoids is 1/4. Let's see, I've got 34 halves. That's 17. Another 17. I have 35 inside here, so I have 35, I think. Yeah, that looks about right. So I get 35/4, okay? 35/4. 8.75, 8 3/4, okay? How good an approximation is this? Well, let's find out, okay? The exact area is the integral from 1 to 3 of this function. The exact area is x cubed over 3 from 1 to 3. We get 3 cubed. 27 over 3 is 9 minus 1/3. We get 8 and 2/3. Okay? This is 8 and 3/4. Okay? That is pretty close. Okay? That is really close. Okay? As far as approximate, only using 4 trapezoids. Very, very close. But there is a more accurate way. A more accurate way to do the numeric integration is with Simpsons Rule. Now let me show you Simpsons Rule. We're not going to derive it. It's just not worth it. Okay, is everybody okay with this? I can do it right on this.
What do we use that for?
In case, if you have to do an area or an integral that can't be done, and there are an infinite number of integrals that you simply can't do, but you need the area, a definite integral, can't be done exactly, you use a numeric integration. That's what it's used for. I had a friend. I did have a friend once. I had one friend once. And he was building a boat, like a sailboat. He had a kit. He bought a kit. Yeah. And he was building this in his garage. And he had to use Simpsons Rule to approximate an area of some part of this boat, like the sail or something like that. It was pretty cool. So, Simpsons Rule. Pretty neat. They gave him Simpsons Rule, and they said, here, whatever the size is that you're doing, you use this rule to get the area, because it was pretty interesting. But that's what Mathematica does. If it can't do the integral, it'll tell you if you just do an integrate, if you do an integral. But if you do an n integrate, numeric integration, it'll use this here as an approximation. Simpsons Rule goes like this. The area is approximately, now this is b minus a over 3n. This is Simpsons Rule now. N would be the number of subintervals. F of x sub naught plus 4 f of x sub 1s plus 2 f of x sub 2s plus 4 f of x sub 3s plus 2, again, okay, plus 4 f of x sub n minus 1s plus f of x sub n. Okay. It goes 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. Okay? The coefficients are different. How is Simpsons Rule derived? It's really kind of interesting, okay? We used trapezoids. We used a line segment connecting these and used the trapezoids to approximate the area under that curve. What Simpsons Rule does is uses parabolas. Takes 3 points at a time and uses a parabola through those 3 points and uses the area under the parabola as an approximation for the area under the curve. It's really kind of cool.
Yeah.
It's kind of nice, yeah. It's kind of cool. It just takes us too long to do, and it's just not appreciated enough by engineering students. That's not right. That's not right to say. But it is true. The results are what matters to engineering students. You know, we need results. Wait, do we just establish this, the math majors here? Any math majors? Did we? What's that?
I don't think we talked about that.
We
I don't think
didn't?
you have any in this class. You mentioned it last
I did
week or
mention it.
something.
I'll probably mention it
No,
every
no,
class
okay.
until I convince one person to change, just to keep me quiet, okay? Lewis, no, huh? Not a chance? No. All right. Anyhow, let's use Simpsons Rule in the same area problem, okay? Let's see how good Simpsons Rule is for this. So for Simpsons Rule, the area in terms of 4 would be approximately equal to b minus a, 3 minus 1, over 3 times n, 3 times 4, f of 1, which is 1, plus 4 f of 3 halves. Now, f of 3 halves is 9/4. We got 4 times 9/4, plus 2 times f x sub 2, that's the 2 squared, 2 times 4, plus 4 times f of 5 halves, which is 25/4, plus f of 3, which is 9. Okay? Okay, everybody okay with this? Good deal? Good deal? Everybody's okay? Ohelia, how you doing? All right? Good. So what do we got? 3 minus 1 is 2. 2/4, 1/2, we get 1/6. We have 1 plus 9 plus 8 plus 25 plus 9. We get the area as approximately equal to 10, 18, 43, 52 over 6, which is 26/3, which is 8 2/3, which I will point out is exactly what the exact area is, okay? It's right on the nose, okay? Which is why Mathematica and computer algebra systems, when they do numeric integration, do Simpsons Rule, basically, okay? It's a Simpsons Rule. Sam?
Why do we learn the trapezoidal rule?
Because, that's a good question. Because we can derive that one, and we can't derive the other one. That's basically it. And if you ever needed to do an approximation, well, if you could memorize Simpsons Rule, yeah, Simpsons Rule is the way to go.
Well, either way, you have to memorize the rules.
No, you don't have to memorize rules. You don't have to memorize either of these two rules.
So basically, we're just going to integrate normally
What's that?
for the area.
If you can integrate normally, that's the way you do it. That's exact always, okay?
Because that's like the easiest way, right?
If you can integrate it, yeah. But there are integrals that you can't do. And there are integrals that Mathematica can't do.
But you're not going to do that for the test.
Oh, yeah, your test, sure. I'm going to put a bunch of them. No, I'm not. Of course not. All right?
That's
All right.
the important
No,
part.
yeah. But you should be aware there is such a thing as numeric integration, because as an engineer, you may have to do something like this, and you'll have a machine that does this. You'll have a Mathematica or a MathCAD or a MATLAB, that stinking MATLAB program, or some program like that that will do it. But you should be aware of what it's doing, just in case something doesn't go right. You should know what's going on. And this is what's going on. It's doing one of these. Brendan.
If n were 3, would the coefficient...
Oh, yeah, you can't do that. You have to have it so it comes out right like this, okay? You can't do n is 3 here. It has to come out 1, 2, 4, 2, 4, 1. So you have to have it come out 4. It has to be a multiple of 4, actually. I don't think you can even do it with 6, can you? Does it come out right?
Is that only for Simpsons Rule?
Yeah, Simpsons Rule, that's only for Simpsons Rule. For trapezoidal rule, you could use n equals 3. But not for Simpsons Rule, because it has to start with n1, 4, and it has to end in 4, 1. Okay? So it's 1, 4, 2, 4, 1. That's okay. That's n equals 4. So could you do n equals 6? 1, 4, 2, 4. Okay? Wait. 1, 4, 2, 4, 2, 4, 1. I guess you could do 6. It has to be even. Let me put it that way. Okay. But you can't use n equals 3. That's a good question. You can't use Simpsons Rule for n equals 3. It has to be an even number so it comes out right. Otherwise, it's going to be messed up. It's a good call.
What is MATLAB?
It's a program that's used by engineers primarily to do computer algebra system stuff. It's a competitor of Mathematica. The interface is, in my opinion, really, it's a difference.
If they put you in tech math, your online is MATLAB.
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 Yeah, MATLAB, yeah. It could very well be. It's typically used by engineers. It's a data thing. It does graphing, though. It does plots. It does solving equations. The bottom line is Mathematica is preferred by math people, and MATLAB is preferred by engineers. Okay, bottom line. Mathematica costs about 87,000 times as much, but it's more elegant. It's the same thing as Apple versus Windows. Mathematica is an Apple thing, okay, and MATLAB is a Windows thing.
Then I probably like MATLAB better.
Okay. You may very well. When you go to UMass as an engineering major, you're going to be using MATLAB. Occasionally, you'll get a person who uses Mathematica, and you may use some Mathematica, but MATLAB is what you probably use.
I was at UMass the other day and they were using Mathematica.
Is that right? That's cool. No, that's good. That's good. All right. How are we doing? Okay. Now, do you guys use any computer algebra systems in your school? None? Use any at your school? No, huh? That's interesting. That's interesting. Okay. Just wondering. Alrighty. Let's go on. What we're going to do, we need to derive a couple more integration rules. We need a couple more integration rules. And we're going to use the integral that we already have, 1 over u du. This is now 5.7, is it? 5.7. Okay. We're going to use this to derive a couple more. The integral of 1 over u du is natural log, absolute value of u, plus c. Okay. That we already have. That comes right from Calc 1. We have the derivative of natural log is equal to 1 over u, so that's right from Calc 1. What we're going to do now is use it to do some other integrals we haven't done yet. First one we're going to do is tangent. We don't have the integral of tangent. We need the integral of tangent. Okay? The integral of tangent. How are we going to do the integral of tangent? Well, what's tangent equal to? Sine over cosine. That's it. Good deal. And what form is this integral? What is it? No. Well, yeah, you shouldn't call it u to the n. You could make a case for u to the n, but n there was -1, which is where u to the n doesn't work. Yeah, this is a 1 over u du form. That's the way you should think of this, as 1 over u du form. Gee, after all, that's what I put at the top of the paper there. You know what I mean? All right, but u is equal to cosine x. Du is a negative sine x, opposite of sine x dx. Okay? I have it. It's right here. Multiply by -1, though. I need to multiply by -1. And then I have opposite of the integral of 1 over u du. There it is. Okay. That's equal to the opposite of natural log, absolute value of u. It's equal to opposite of natural log, absolute value of u. U is cosine. That's the integration form for tangent. Now, you could take this negative outside and bring it up front as an exponent and make it the natural log of secant, because it becomes 1 over cosine, which is secant. Some books actually use natural log of secant. When I use it, it's going to be negative natural log cosine, okay, as opposed to a natural log of secant. Let's generalize this x integral, so it's in terms of u. The integral of tangent u du, u is a function of x, is equal to negative natural log, absolute value, cosine u plus c. This integration form I would expect you to know. Okay? This gives us another integration form immediately that I would not expect you to know. I would not put this on the test. And that's the integral of cotangent u. Just not worth you memorizing, but you should know this. There is a trick, and I think I mentioned this along the way, that works for derivatives and integrals when you integrate this co-function. Wait, was that a question? Go ahead. Oh, all right, you sure? You had your pencil kind of. All right, okay. All right. The integral of its co-function, cotangent, okay? What do? You take the opposite of the co-function. It's going to be the natural log, absolute value of sine. It's a trick that works for trig functions when you take derivatives and integrals. If you know the integral of tangent, you automatically know the integral of cotangent, its co-function, by taking the opposite of the co-function. Okay? That's a little trick that works. I'm not going to ask you this one. It's just not worth memorizing. But you should be aware of the trick, though. So I'm kind of contradicting myself, but I don't know. I'll figure it out. All right. So if you had to do this integral, let's say from 0 to pi over 4, tangent of, yeah, we could do that. Okay, let's not though. Tangent of, how about x over 2? No, we don't know that. Oh, rats. Okay, I want to do one that, tangent x dx. Let's just do it. All right, the integral of tangent, negative natural log cosine, 0 to pi over 4. Okay. This negative you can keep on the outside. Cosine of pi over 4. I would expect you to know that. Thank you. So you get the natural log square root of 2 over 2. Okay. Minus cosine of 0. 1. Good. But what's the natural log of 1? 0. Good. So you end up with a negative natural log square root of 2 over 2. Okay. It's kind of an easier one, but that's I got to tell you, that's the kind of thing you'll see on the test, okay? That's a possible test question. All right? All right, integral tangent then is added to our list of integrals. We've got another one to add. Everybody else set with us? Yeah. Okay, you all set? Everybody's all set? Caroline, how you doing back there? Okay? Let me figure. Never mind. Okay. All right. Another integral we have to do that we don't have yet is the integral of secant. Let's do the integral of secant. Well, I got to tell you, this is a trick to derive it. I wouldn't expect anybody to come up with a derivation here. The trick is to do the following. You're going to multiply numerator and denominator by secant plus tangent. Wow. Okay. Why do such a thing? Well, because, we multiply by secant plus tan over secant plus tan. We multiply by 1, so we didn't, we're allowed to do that. But why did I do that?
Because that equals 1 on top.
Because what?
Secant, when you multiply it, it will equal 1. There's
No, it won't equal 1. Secant squared plus secant tan, is that what you're saying? If I multiply it out, is equal to 1?
Is there an application like that?
Well, tangent squared plus 1 is secant squared. But it's not secant squared plus secant tangent equal to anything.
No, we're close.
Yeah, it was close, yeah. Why do such a thing?
Because those are
Because,
secant squared and tan secant. Secant squared is the derivative of tangent, and then secant tan is the derivative of secant.
perfect. Very nice. Nicely done. That's exactly right. Now I have a 1 over u du form, okay? U is equal to secant plus tangent. The du is equal to, the derivative of secant is secant tan, I got them reversed there, but anyhow, secant x, tangent x. The derivative of tangent is secant squared. And believe it or not, that's what I have in the numerator. That's exactly what the numerator is. It's the derivative of the denominator. I have a 1 over u du form. Okay. That's perfect. Okay. The integral of which is natural log absolute value of u, which is the natural log absolute value secant x plus tangent x plus c. Therefore, the integral of secant u is equal to natural log absolute value secant u plus tangent u plus c. Okay, that's yet yes, Brendan.
Am I missing something? Why is secant? Why can't you just write it as 1 over cosine? And have that.
You could. Here's what. Okay, first of all, this is the integration form. Now let's look at Brendan's suggestion. He says, write it as 1 over cosine, you bozo guy. Okay? Do it that way. Now what do you want to do?
That's 1 over u.
What's u?
Cosine of x.
Yes, it is. What's du?
Negative sine of x.
Where is it?
Oh.
You don't have it. That's the problem. Okay? That's a good idea, though. That was a great idea. If you're thinking, that's for sure. Yeah, you just can't do it because you don't have the sign to go with it. And you can't get it from anywhere. It's not like you can multiply by sine and multiply by 1 over sine. So, this is another integration form. It also gives rise to the integral of cosecant u, which I'm never going to ask you. But what would the integral of cosecant u be?
Would it be natural log cosecant cotangent?
Yes, and it's a negative on the outside. Yep. Take the opposite of and replace it with the trig functions, with the cofunctions. Okay? And that's exactly what it is. Okay? That's exactly right. Okay, but I'm not going to ask you that. So, integral of tangent, negative natural log cosine. Integral of secant, natural log of secant plus tan. You should know those two. Okay? Those are two additional integrals that we have. We only have a couple more integrals to go, and then we have all our list of integrals. But there's more to this 1 over u stuff. Okay? Let's suppose we have something like this. Let's suppose we have x plus 1 over x minus 1 dx to integrate. Well, it's not any of our integration forms right now. Okay? But there is a technique that we can use to get to one of our integration forms. And that technique is to divide. Do a long division on this. Okay? All right. You don't like that, Jim?
Because we're about to, it's not synthetic division. It's the,
Well, you could use synthetic division, actually, since these are just linear factors here. But we're going to actually do the long division because you're going to have to use long division at some point. So let's do it. X plus 1 divided by x minus 1. Just do a long division. Okay. What times x is x? 1. Subtract 1 minus a negative 1, 2. This becomes this integral. 1 plus 2 over x minus 1. Okay. Well, what about that integral? Can we do this integral? What's the integral of 1?
No.
Excuse me? What is it? What'd you say? 4?
Nothing.
You said nothing?
X.
X plus. Now, what form is this integral here? Let me write it out. And that's exactly what it is. What is this integral? You can take the 2 out front, of course, and it's 1 over u du form. It's our natural log form. Okay? U is x minus 1. I'm going to write it out. The du is dx. Du dx is 1, so du is dx. So we have x plus 2, the integral of 1 over u du. Okay? U is equal to x minus 1, du is dx. This is 1 over u du. You can take the 2 out front. So, x plus 2, natural log, absolute value of u. We'll see. Okay? How are we doing? Here's the rule. If the numerator, if you have a rational expression like this, rational expression, where the degree of the numerator is equal to or greater than the degree of the denominator, do a long division, okay? And then integrate the remainder. Hopefully it'll be a 1 over u form. The ones we'll see will be 1 over u forms. Okay? Later on, when we do integration with partial fractions, we'll be able to do something else with these as long as we can factor things. But right now, this is what we got. So, let me give you guys one to do. Okay? Here we go. Let's do the integral of. How about x cubed plus 4x squared plus 3x plus 5 all over x minus 2. Go ahead. Oh boy, oh man. Got this, Brennan? All right, okay, pretty good. Got it? You got it.
I don't know.
You don't know? All right. So that the big meet is when? Tomorrow or next day? Soon, right? State meet?
Oh, yeah, it's tomorrow.
What's that?
It's tomorrow.
That was good. Article, paper. Okay, how are we doing? Jacob, what do you think? You have it?
No, not yet.
No, not yet. Ooh, okay. So, some people still work. We'll give them another couple minutes. Which time shall I go? Okay, who wants more time? Oh, okay. So we're going to meet Tuesday.
Oh, not quite.
Yeah, Tuesday afternoon.
Wait, I thought it was scheduled for that.
What's that?
The week after is the test?
No, February 29th. Is that the week after? Is it? It's like
No, so
2
it's 14 days.
Yeah, yeah. I believe it's the 29th is when the exam is around. Is that a Monday, the 29th?
I don't know, I just remember seeing.
Yeah,
The
I think-
first meeting is on like the 15th or the 16th.
Yeah, 16th, and then we have another practice, and she put up some a past exam up there. Check Blackboard. Check it out. Math team practices Tuesday. You like doing math problems, you know?
Just pizza.
And there's pizza. and there's pizza and me, in that order, okay? And so, yeah, it's good stuff. It'll be Tuesday because of the Monday schedule thing. 12:15. Brendan, what are you doing during the day? You do anything during the day? During the day? Yeah, if you want, if you feel like it, right? You could take a day off or two, right? Tuesday, think about it.
Can't be here, sorry.
What's that?
Not gonna be here.
You're not?
No.
Are you actually trying to get someone to play hooky to come to Mac?
No, I wouldn't really.
Wait, what time is this at?
What time is the test?
No, the meeting.
Tuesday at 12:15 during Peloton. You should come. 4:06.
It's at 12:15. How long is it?
45 minutes, maybe? Half an hour, 45 minutes. Yeah, something like that. We
The
have
way my
pizza.
block schedule is arranged now, I have a study before that, before my lunch block.
Well, you should do it.
Might be.
4:06. You guys on math team? You both are?
No, I got kicked out.
You got kicked off? Wow, that's pretty serious. You are? But you used to be before you...
No, I wasn't smiling.
It's hard to do. But anyhow, wow, you guys have school too, though, huh? You're committed to that school thing over there? Yeah. Oh, well. All right, how are we doing? Let's take a look. All right, we have an integral. The numerator has degree 3, denominator has degree 1. The rule is to do a long division and then work on the remainder. So let's take a look. We'll do a long division. X cubed plus 4x squared plus 3x plus 5 divided by x minus 2. We could use synthetic division on this as well. In fact, maybe I'll do that too. All right. You say x, what times x is x cubed? That's x squared. Multiply it. Subtract. Bring down the next. Okay. What times x is 6x squared? It's a 6x. Subtract. Bring down the next. Okay. What times x is 15x? 15. Subtract. That's your remainder. So this integral becomes this integral. X squared plus 6x plus 15 plus 35 over x minus 2. Okay. Integrate it. X cubed over 3, 6x squared over 2, 15x. This is a 1 over u du form. So we get 35 natural log absolute value x minus 2. Okay. And that would be your answer. You should be aware of a synthetic division on something like this. Let me just show you that quickly here. And we only have a couple more things to do and then we're going to be done. So, what do you do for synthetic division on this? You write the coefficients. You take, what you're doing is testing to see if 2 is a root. You use 2, okay? Whatever makes that linear factor 0, okay? You bring down the 1, multiply, okay, 2, add, multiply, add, multiply, and add.
Oh, we have the same number.
Yeah, that's exactly what happens. You get a 1, a 6, and a 15. Those are your coefficients of the quotient, okay? And the 35 is your remainder. So bring it down, multiply, add, multiply, add, multiply, add, and you're done. If this comes out to 0, then you know that x minus 2 is a factor. 0 is a root of that equation. It causes it to be equal to 0. Okay? So that's the way to do a problem like this if you have that simple linear factor. And that's all you're going to have are the linear factors down there. So it should be You may be able to use that in the homework and save yourself some time anyways, a little bit of time. All right, there's 4 problems we have left to do.
I have a question.
Yes, go ahead.
So just, it kind of got me lost just looking at it. So the first step during the division, where you multiply through by the x squared, and then you get x to the third minus 2x squared, and then you're subtracting those. Where does
What, up here?
Yeah, right.
Okay, x squared
Yep.
times x is x cubed,
Yep.
and x squared times the 2 is 2x squared, and it's minus.
Yeah. So why don't you subtract it from the?
You do. You take x cubed minus x cubed is 0,
0.
and then you take 4x squared minus this negative 2x squared.
Wait, where's? Oh, okay.
Yeah, you got to be careful of that.
Yeah.
Think of it as plus a negative 2 if you want, but you have to subtract the negative 2 from 4
all right, right
to get
there.
6.
It's
Yeah.
next to me.
Yeah.
Yeah. All right.
Yeah. Common mistake right in there. All right, we got 4 integrals to do here. The 4. We're going to do the integral of 1 over x squared plus 1. The integral of x over x squared plus 1.
Oh, we're doing this one.
Yeah, you guys are going to do these 4. X squared over x squared plus 1. And x cubed over x squared plus 1. Okay? Go ahead. Take a few minutes and do these 4, and then we'll do these 4.
So we can't move variables out.
Correct. Levi, you have them all? You have them? Out of way. Wow. All right, hurry up, the rest of you guys. He's waiting for you. He's getting impatient. No, he's not getting impatient. Carolina, were you here when I said when your next test was? It's on a Monday, and that's okay then, right?
Yeah. What day is it?
It's Monday the, what did we say?
22nd.
22nd. Okay, what you're allowed to do in this, the exam too, you may have a scientific calculator only, okay? We have banned phones from tests, okay? So don't expect to use your phone as a calculator, okay?
What happens when calculators get as smart as phones?
What happens when what? Oh, when the calculators get as smart as phone, which should probably happen. Then we'll have to ban those things too, I guess. I don't know.
No calculators.
No calculators. Actually, on my test, you shouldn't even need a calculator. You shouldn't even need it.
You know, what's really funny is like as a joke, like at a final, like all the kids are coming in and take all their calculators and start handing out abacuses.
That would be funny.
I
That would
like
be pretty
that.
good.
This is a good one.
Yeah. Yeah. I mean, when you can take your phone and take a picture of a test question and go to a site and it'll just do it for you. I mean, the heck? You know?
Who even needs to take the class anymore?
Yeah, I know it. I know it.
And then the internet crashes. And like that.
Ooh, then you get some problems. Carolina.
Are you gonna do like a review before?
Yeah, we had a little discussion about that. I was reluctant to do a sample test kind of a thing because students would focus on those questions only to the neglect of everything else. But I'm trying to think, in this first one here, you know what's going to be on there. There will be a bunch of integrals. That'll be the bulk of the test. There may be a position one. I think I have one of those where I'll give you the position. You have to determine the velocity at a given time or something like that, or how high the thing is tossed. But the whole thing is integral, so I may just give you a list of integrals to do in one of those problems. Yeah, I may do that. Give you like a sample test to do, and we'll go over it.
And that's gonna be on Thursday, right?
That'll be on next Thursday, a week from today. And I'll also go over the lab at that point. We're going to finish everything Tuesday night because Tuesday night is a Monday schedule. Is that okay? It's not okay? What are you doing Tuesday night? You have something Tuesday nights?
I have physics on
Well, you won't. If it's here, you won't have it.
No, it's at.
It's where, oh, yeah, that's right. It's at Bay Path.
You can relate this to you, but to actually.
I'll have to call up Bay Path and tell them to change your schedule around. Okay. Oh. This is what happens when they do this kind of thing, where Tuesday is a Monday night. And people have lives and they have other things scheduled on those days, and it's a problem. What I'll have to do is email you or something, the sample test or something. We'll do something. Yes, Ed.
When is the new deadline for the
Pardon?
new deadline for the homework?
Oh, yeah, the new deadline. I'll move it up a week. That's a good call. I forgot about that. Somebody's going to remind me, right?
The day of the exam.
Yeah, sure.
So,
You should, you know what you should do?
do the
No, I'll make it Friday of that week.
All right, so the 27th.
27th?
Sorry,
That's
26th.
26th. That's what I'll do then.
You
I'm
should-
going to make it the 26th.
I mean the 19th. Sorry.
Maybe I'll check it out myself and I'll figure out when it is.
You should get Devin to set up a website for you.
Huh?
You should get him to set up a website for you.
To do what?
The YouTube channel. You post the videos on the website and any documents you need, like all the practice tests.
We're going
They
to.
get
Yeah.
really deep competition.
The notes, the lectures, the tests, the lectures are on YouTube, are getting on YouTube. You should be aware of that. If you go to YouTube and look up Calculus Burns STCC, the lectures will be up there. What's so funny about that? Why is that amusing?
If you give grammar and say Professor Burns calculus.
Oh, maybe he put it out. I don't know what he put. He put
Well,
something
Rick
like that.
said it's Calculus Burns SGCC.
Yeah.
That's not what he actually put in.
So calculus is burning SGCC.
Oh, I see. Oh, I got a little thing in my name. I got it. All right. That's okay. I can see that. Are you doing it right now? You on YouTube?
Oh, you're talking to me?
Yes.
Oh.
Oh, you're somewhere else. Oh, you're checking out something else.
Yeah, I'm at YouTube.
Okay, do a search on that.
It's Professor R.Burns as calculus stuff.
Oh, okay. I knew he had something like that.
Yeah, Professor Burns calculus.
Yeah, just what you said. Okay. Yeah, and he's putting up the lectures on there. So, I don't know, he may have one or two because that's all we've done so far, but he doesn't have the one from last Thursday yet because I just gave it to him tonight. So, that'll get up there. So, if you do miss a class or if you want to see the lecture again, you know, for some reason, you want to listen to me do it again.
You got 3 subscribers now.
What's that?
You got 3 subscribers now.
I have subscribers? That's good then, right?
3 now.
3 of them?
Sometimes.
Wow.
13.
Wow. 13 now?
What?
Oh, it's going up
Oh,
exponentially.
that's the views, not the
No,
subscribers.
Oh, you got me all, oh, man. Had me all psyched. I thought I was going viral. Oh, man.
You can name it might gonna go viral.
Yeah.
Yeah,
Oh,
person
yeah.
Burns.
Might make some headlines.
Yeah. Yeah.
That should be extra credit if we subscribe.
Yeah, there's an idea. Well, I got to do is get my grandkids to all subscribe and things like that. Yeah. All right. Yeah, so they're going to be on there. So that could be helpful if you have to miss a class. Yes.
You put closed captioning in your video.
What?
Closed captioning.
Closed captioning.
Yeah.
Subtitles.
What?
Subtitles.
Subtitles.
Yeah.
What? Subtitles.
It automatically does, right?
What? So people all over the earth, people in China can look at them and
Maybe, like, one
Yeah,
video
I see.
on this video, you know.
closed captioning too. Wow.
Yeah, you should.
Wow.
I read.
That's cool. You know how to do that? You could put it on there?
Yeah, I think you go to your videos and you go. Well, you got the you have to give us like a permission to like do it. Edit.
Really?
Yeah.
I give you my permission. You can do
No,
it.
but you have to like open it. I don't know.
Oh, boy. All right. Well, anyhow, they're going to be up there, okay? They'd be better if they were edited somewhat, and like this conversation would be edited out, you know, that kind of stuff.
This is like the meat. All that math is,
Yeah,
red.
forget it, yeah. The boring stuff. All right, you guys ready or what? Caroline, what are you laughing at?
Your closed captioning is like way up.
I don't, what do you mean? I don't understand. I have,
And it's like you're like distracted and then like, I don't know, just.
me get distracted? Are you kidding? I am constantly distracted. All right. All right, let's take a look at these 4. First one. What is it?
Natural log x squared plus 1.
No.
X cubed over 3 plus
What is it?
x cubed over 3 plus x.
No. No.
The natural log of x squared plus c.
No. No, here's the deal. Here's the deal. If you let u equal x squared plus 1, which is what you would think you would do, the du is 2x dx. You don't have that. You don't have that 2x. You can't do this. It's not a 1 over u du form. What is that form? We've had this form. This is an inverse tangent form. This is arctangent inverse tangent x. We're going to generalize inverse tangent next time, where we're going to have a u squared plus a squared. We're going to, instead of a 1, we'll have a constant there. It'll be a pretty easy generalization. But that's inverse tangent, okay? That's inverse tangent, arctangent. Okay, now, what is this one?
1/2 natural log x squared.
That is perfect. 1/2 natural log. Now, in a problem like this, you don't even need absolute values because x squared plus 1 is always positive. So the proper thing to do would be put it in parentheses. I mean, the absolute values are not wrong, they're just not needed, because x squared plus 1 is always positive. Now, this is a 1 over u du form. U is x squared plus 1, the du is 2x dx, multiplied by 2, multiplied by 1/2, it becomes 1/2 the integral of 1 over u du, which is this natural log. That is a natural log one. What about this one? What is this equal to? Yes, Brendan.
X minus 1 over x plus c.
X minus 1 over x. No, Brendan, that's not it.
Would it be,
Yeah, I like the x part, but what?
1/3 x to the third?
No. Let's take a look at this, okay? Let me go to another page, so I have some room here. Anybody else want to get his or her opinion in here, or 2 cents in here? X squared over x squared plus 1. First of all, what's the rule when the degree of the numerator is equal to the degree of the denominator? The rule is to do what? Divide. So let's do a divide. There's a little trick for this too. I'll show you that in a minute, but let's do the division. It's x squared divided by x squared plus 1. X squared times 1 is x squared. And subtract. So this becomes 1 minus 1 over x squared plus 1. Okay? Okay? There. So the integral of 1, x, which is what Brennan said. But what's this integral? We know that's an inverse tangent form. Okay? So that's what it is. There is a trick for doing this. When these are of same degree, the trick is to add 1 and subtract 1 to the numerator. You can add 1 and subtract 1. What are you doing? You're adding 0 to the numerator. You're not changing the value. What does this give you? Well, if you think of this over this, I'm going to split it up into 2 parts. This over this is 1 minus 1 over this. What it does, it gives you the same thing as you had over here without actually doing out the long division. It's just a little trick that you can sometimes use when the degrees are the same.
You're
Okay?
not allowed algebraically to split it into 2 parts originally, right? Or you can't-
Originally, you cannot. You cannot split across a denominator, but you may certainly split across a numerator. Okay? Okay. That was 3. Number 4, you really have no choice in the matter but to do the long division first. Let's do it. It's x cubed, okay, divided by x squared plus 1. X squared times x. Okay, x squared times x is x cubed. Subtract. We have x minus x over x squared plus 1. The integral of x is x squared over 2. What form is this one here?
Which is half log x.
Yes,
Yeah.
it's a 1 over u du form. Okay, where u is x squared plus 1. The du is 2x dx. Multiply by 2 and by 1/2 to get 1/2. You have the integral of 1 over x squared, 1 over u du, natural log x squared plus 1, okay, plus c. Okay. Everybody see those okay? One more thing I should mention. Sometimes these things are disguised. I mean, you may have something like this. What form is this? What form is it? Yes?
X squared over x squared plus 1.
That's not a form. Okay? I want to know what form it is.
Oh, you're going to have e to the 2x plus minus, or plus, or no, I'm sorry, minus 1 over 1 plus e to the 2x?
No. Besides, I want to know the form. Leave by.
Oh, 1 over u du.
Thank you. That's exactly what it is. It's 1 over u du form. U is equal to 1 plus e to the 2x. Du is 2e to the 2x dx. Well, that's okay. We can multiply by 2 and by 1/2. Giving us 1/2 the integral of 1 over u du. Okay? This is u. This is the du right here. Okay? Where did that e to the 2x go? It's in here, in du. Okay? This is 1 over u du form. The answer is 1/2 natural log. I don't need absolute value here because 1 plus e to the 2x is always positive. Sam, what's up? That's your answer.
So when your du is something that you don't have, and then you can add in the constants on the outside and inside to balance it.
Yes.
How come you can't also add in a variable? Like
Because as soon as you multiply by a variable and take a variable out, it's different than what it was to begin with. It's changed.
Okay.
It doesn't work. You're just going to have to accept the fact that that simply doesn't work to have that variable on the outside. It's now a different integral. Constants are okay. Variables are not. Okay. Okay. All right. I better give you one more. That was not good. I was expecting better than that. Here, let's try this one. You guys do this one. How about the integral of cosine x over 1 plus sine x dx. Here's one, and let's do this one too. Cosine x over, let's just do the forms, okay? Sine squared dx, okay? Let's, the first one. What form is this one? What form is it? It is. It's 1 over u du form. U is 1 plus sine. The du is cosine x dx, and that's fine. We have a cosine x dx. That integral becomes 1 over u du. Okay? Natural log, absolute value of u, natural log. And again, you don't even need absolute value there because 1 plus sine x is always greater than or equal to 0. But anyhow, natural log 1 plus sine x. What form is the second one? No. It's a good shot though, Jimmy. What form is the second one? Yes, thank you. It's a u to the n form. U is 1 plus sine. The du is still cosine. But now the integral is 1 over u squared du, or u to the negative second du. It's a u to the n form. Okay? You're going to be better off, I'm telling you this, if you think in terms of these forms. We have about 12 forms. Every integral that we do right now will be, you'll be able to change it to one of those 12 forms. Now, sometimes you're going to have to do something. The other day we had these things, which is none of our integration forms, but we were able to change this by letting u equal, what did we do here? That was last week. What did we do here in this one? Let u equal, yeah, the square root of x plus 1, anyway, Carlos. And solved by squaring both sides, solving for x. This is different than what I'm talking about over here. What I'm talking about here is looking at it and seeing that you have a u to the n form or 1 over u du form. This one, you don't have those forms. We're making a substitution and changing the integral around in hopes of getting something we can integrate. Okay? As opposed to looking at this and saying, oh, this is u to the n. This is 1 over u form. Dx here, 2u du. And then we made these substitutions. We changed this integral into u squared minus 1, that's x. Square root of x plus 1, that's u. dx is 2u du. This is different. This is, I'm telling you, this integral does not belong in this chapter, but they stick it in this chapter over my objections, okay? They didn't care about my objections. This really belongs 2 chapters hence when we do techniques of integration, and we do integration by parts and partial fractions, but they stick it in here. Anyhow, but all the other integrals that you do, you've got to be able to say that's u, and here's a du, and I can get that du with at most the introduction of a constant. Okay? Now sometimes you have to do a long division first. Sometimes you have to do something first, okay, in order to get that integration form. But you should be able to do it. What do you think? Oh wow, people are dead. You guys are just plain dead. Oh man. Oh gosh. All right. So, oh geez. All right. No offense. No, I'm only kidding. So here's what you should be doing for homework. Whatever this is. This is what is this, Jacob? 7. Okay. 5.7. Okay. And next time we're going to finish the chapter. Okay. So do the homework. Get the homework done. We'll finish the chapter next time. Time after that, we'll review and do a lab, and then your test is the Monday after that. Oh, wow, man. Dylan, I'm working like a dog up here, man. I'm working like a dog. What's that? You can tell? Yeah.
I'm not going to be here for either of the classes next week. My school's on break.
You going away?
Yeah.
Where are you going?
Hawaii.
Oh my gosh, really? What island? Honolulu is the capital in the city. It's on Oahu.
Yeah.
You've got to climb Diamond Head. You got to, if you're really brave and in good shape, you can do the Cocoa Head climb. That's all right. It's a railroad track that goes up this mountain like this. It's unbelievable. But anyhow, yeah, it's a good place.
So I'll try and watch those videos if they go up.
Oh yeah, yeah, cool. All right, yeah, you won't have a problem. See you. Have a good time. See you, Sam.
Can I just grab your notes for a second? This out some parts.
All right, what was I doing now? Somebody was going to remind me to do something. Amanda, what was I doing? Oh, the dates for the homework. The first page. See it, Chris? That's where it was. You had it.
Yeah, that was for Monday.
Oh, yeah, I remember this now. We were looking for it. But that's all right. We got it now. Good deal.
What about the one for last week?
What's that?
Last Thursday?
Thursday?
Take a picture?
Sure. Is that this? That's this one, right?
Last week.
2/4/16?
Yeah.
Yeah, I will not be coming on Tuesday.
Okay.
Yeah,
I'm going to do the inverse trig functions, and I'm going to do.
It's a big thing, right? I'm going to Wisconsin.
Okay.
This weekend. So.
Well, see what you can do. We'll get the video up there, hopefully, and you can check that out. Okay.
You're still recording. Just so you know.